So in this module, I want to take what we've just learned about Bragg's law and apply it and see what a real diffraction experiment looks like. So I want to show you the setup first. So this is a pretty typical X-ray diffractometer, the actual experiment, the actual equipment. That's what we call it, diffractometer. This is the actual setup. And I know it looks kind of old, but it's just a really simple diagram showing you what this experiment would look like. So let's kind of go through the details here. So let's start with the first thing. So over here, you see that it says copper target, and then you have a culmination, and then basically this whole thing is about producing X-rays. And so what we can actually do is if we bombard copper with X-rays, or sorry, if we bombard copper with electrons, it will actually produce X-rays. And those X-rays have a very specific wavelength. And then we can do some additional filtering and so forth, which is what's happening here, and we'll get our X-ray source. So we don't need to know too much about that, but we have a filter that separates the different wavelengths. And so we just want one wavelength. And so that's typically known as the K alpha wavelength. And since it is only one wavelength, we call that monochromatic for one wavelength. All right, so that's the source. So this is that, incident beam that we've been talking about. It's generated here. So then that beam is directed at our target or sample, right? Excuse me. So this is the material that you want to know its crystal structure. And so that is aimed here. And we've angled this in the diagram here so that you can see that the angle here and the angle over here with respect to the incident beam and what would be the diffracted beam is theta, right? So the theta geometry that we saw in Bragg's law is applied here. And so from the target, if we again go at an angle theta, and we see up here, any diffracted beam would then hit this detector. Okay, so our target hits the material, and then next, the X-rays reach the detector. And so we don't really need to know how that happens, but basically they interact with this material and are counted as intensity, right? So the more that hits this detector, the more intense the signal is at that angle. And so this whole geometry happens, but we don't just do one angle. What we actually do is we rotate. We change the angle theta so that we can run the experiment at different values of theta to see what happens. However, what we should keep in mind here is that if we're comparing this geometry, what happens is the target, the X-ray source, is typically stationary. What we do is to rotate this, we rotate the target or the sample by theta, and then we actually rotate the detector. So this kind of scan arm here, we rotate that by an angle of 2 theta. And that's what allows us to keep the theta geometry here. So by moving the detector by 2 theta, it allows us to maintain the geometry because this doesn't move. So instead of moving both, we only move one thing, and that's the detector. And to do that, we have to move it by 2 theta. So that's why in the previous example, I mentioned that the experimental data that we get is actually in terms of 2 theta, because the instrument that measures the angle is measuring the angle between the target and the detector here, which that angle would be 2 theta, as you can see labeled here. And so all of this then all of this then goes to our kind of computer, or in the old days, it would be a chart recorder where we would measure the intensity as a function of 2 theta. And that's what we'll see in the actual data. All right, so just a side note here about the X-rays, right? Because we typically just refer to these X-rays as the incident beam and then just move on. We know the wavelength and we can just move on. But a little bit more onto this, because we're going to talk about this in a later, or this kind of calls back to our study of the atomic structure. is that these X-rays that we produce, the most typical X-ray used is known as copper K alpha, and that's a specific wavelength, a monochromatic wavelength, and we get that when that electron, basically that there's a high energy electron that hits the copper atom, and what it does is it knocks out an inner electron from one of these inner shells. So, for example, an atom or an electron here in the K shell. So what happens when you knock out one of those electrons is it becomes kind of unstable, right? Because there's a low energy electron in the K shell missing, but there's electrons in the L or M or N shells. And so that vacancy here will be filled by an electron in one of these other shells. And when it does that, this higher energy electron, for example, let's look at this one. So let's say an electron in the N shell then fills the vacancy in the K shell, right? This would be much higher because it's further away from the nucleus. And so that will reduce the energy, and the energy difference will basically liberate energy because it's lowered the energy of the atom. And so that difference in state is quantized, as we know. And so that difference in energy between the N shell and the K shell will give us ejection of energy at a very discrete level. And in this case, the energy level is on the order of X-rays. So what we get is we get an X-ray of a very specific energy or wavelength. And so that's how we get it. We get it from interactions of high energy electrons with our sort of target in the X-ray generator. And so that's just a little bit more about how that's done. All right, so let's go ahead and look at kind of the results of this experiment. Like I said, we're gonna basically plot the diffraction angle 2 theta. So that's the angle between the X-ray source and the detector, and then intensity. And so this is how many X-rays are produced. So you see down here at the lowest angles recorded, we have a very minimal number or minimal amount of intensity of X-rays. So basically there's always some level, very low level of X-rays that are just kind of floating around, right? That's known as our background. So you kind of see it's jumping up and down here a little bit, but this is kind of our background. So all of this down here. So that keeps going, and so we start at 20, and then we keep scanning to record this data, and we go up to 30 and 40, and we keep scanning, and nothing's really happened yet, right? It just looks like a very ragged line. So nothing's happened. However, once we get here, so this is about 45, you see that the intensity shoots up, right? And actually forms a peak and then comes down. So it's a very narrow peak that we see here. And then it keeps going, nothing happens, and we see another peak in intensity, and then another peak of intensity. So what's happening here is when we're at an angle such as 30, excuse me, all of those X-rays from the source are in phase, but at that angle, when they interact with the material, they come out and they're destructively interfered. Right? So all of the amplitudes basically cancel each other out. And so we get a very low level of X-ray produced. However, at these very specific points, like here, here, and here, we get intensity. And so at these points are where we see the X-ray intensity jump up, because we have constructive interference, and another name for that is diffraction. So diffraction is occurring at these specific angle values, like a little less than 45, right here at 65, and then 82 or 83 or so is where we have diffraction. So these are our Bragg angles, and we can determine, using Bragg's law, we can plug in the angle and our wavelength of the experiment used, and we can determine spacing. So what that means is that each one of these peaks corresponds to the spacing between a given set of crystallographic planes. So they're already labeled for us here. So you see that this first peak It's labeled. At this angle, we see diffraction from the 110 set of planes. So those are causing constructive interference at the given angle that we see. And then here, it's for the 200 type of plane. And for here, it's the 211 set of planes. So each one of these corresponds to the spacing between each plane. And so here, I'm just kind of showing you the 110. This is what the 200 would look like. And then this is the 211 plane. So each one of these very specific peaks refers to diffraction occurring from constructive interference of specific diffracting planes. All right, so this is the data. This is what's allowing us to determine the structure. So what we need to know now is the relationship between these planes, so the 110, and the overall lattice parameter, right? So that we know what our edge length is, right? So what the crystal looks like. And so if we're talking about a cubic system, we have this specific relationship where the d-spacing of a plane is related to the lattice parameter divided by the square root of those indices. So h squared plus k squared plus l squared. So this is a very specific relationship we can use for the entire cubic system, which is useful. So if we basically, from a peak, we'll get an angle, and from Bragg's law, that will give us the d-spacing. And then from there, we can determine the lattice parameter. That's the kind of the power, and that's how we determine crystal structure, is we use this information from diffraction to be able to determine the shape and the size of a lattice. Excuse me. So for other systems, we can also derive expressions that relates the d-spacing to the indices and also the lattice parameters. So for hexagonal, we know A and C. So this is a more complex relationship. For tetragonal, we see that D is related to A and C and also the indices. And so same thing with orthorhombic. So we can identify relationships for all of these, but for most of the calculations we will do, we're just going to be focused on cubic.